Just a reminder, your test is in 1 week. Transformers, no, not the movie. What's a transformer? It's an electrical device. What we do is we have a laminated iron core shaped kind of like that. And then we wrap some coils of wires, a certain number. In fact, we're going to call the input the primary side. We'll use subscripted P for primary. We have a certain number of coils of wires. We have an input voltage. On the other side, we have a different number of coils of wires. We call this the secondary side. What happens is this: if we hook this up to an alternating current, if I use my right-hand rule for that solenoid, because that is a solenoid right there, what'll happen is I'll get a magnetic field pointing up, pointing down, pointing up, pointing down, pointing up, pointing down, pointing up, pointing down, really fast, 60 times a second. That's a changing flux. We have the iron core because when you expose iron to a magnetic field, it amplifies the magnetic field because it acts like an iron. So it, I'm going to use air quotes, transmits or conducts that changing flux to this particular solenoid. Now this solenoid is experiencing a rapid change in flux. You know what that means? We're going to get an output current induced, an output voltage induced. This is how we can transfer current from one place to another without actually transferring electrons in between. If you have wireless charging, it's being done through a transformer. And what we can do by changing the number of coils of wire on either the primary or the secondary, we can change the secondary voltage, we can change the secondary current. So the input side is usually called the primary. I'm going to use a subscripted letter P, and the output is going to be the secondary. I'll use a subscripted letter S. Transformers only work with alternating current, not direct current. The alternating current produces a sine wave current, and what you get is a rapidly oscillating magnetic field, up and down, up and down, up and down. You get a massive change in flux, and Faraday's law kicks in. So the changing current produces a changing magnetic field. We can say, hey, that's going to be a delta flux. The iron yoke help to transmit that magnetic field to the secondary coils, and the changing magnetic field passing through the secondary coils induces a voltage, and if we hook it up to a circuit, now we've got current. Would a transformer work with DC current? No. Why not? No changing flux. Transformers are all over the place. For example, in our houses, we get, I wrote 110, it used to be 113 points. It's 120 volts coming out of your outlets. But most of your devices can't handle 120 volts. So my laptop that's sitting here, for example, because it runs off of batteries, there's no way it runs on 120 volts because the batteries can't put that out. Probably runs off of 12 volts or 6 volts. So anytime you plug in a device and you see one of these big squarish adapters, that's a transformer. It's stepping down the voltage from the 120 source voltage to whatever your device needs. So if you ever have one of those big blocky plugs, when you plug it in that looks like that, that's saying, yeah, we're getting 120 volts input, but now we're only passing out 6 volts. We're transforming the voltage. Also, those big gray barrels that you see on telephone wires that look like a big barrel, those are transformers. In the power lines in your neighborhood, typically they're running about 20,000 volts. Your houses can't handle 20,000 volts. So every 3 or 4 houses, there's a transformer that steps down the voltage to 120. If you go look, you'll see, oh yeah, there's wires going from that transformer to house A, house B, and house C. All 3 of them are splitting that 120 volts and that current. Or if you live in a neighborhood where they don't have power lines, where the power is buried underground, you might see those shiny metallic looking boxes. They're often yellow colored. Those are transformers as well. So they're seen on power poles, they're seen on green metallic enclosures at ground level. You can also see there's a couple of power stations along Dudney Trunk Road. Those are step up or step down, probably step down transformers as well. How do they work? quite nicely. Here is the transformer equation. The number of coils in the primary divided by the number of coils in the secondary will equal the voltage in the primary divided by the voltage in the secondary. Oh, but it will also equal the current in the secondary divided by the current in the primary. Write it down very carefully. Notice primary coils goes with primary voltage, goes with secondary current, because when voltage goes up, current goes down. And then can you find where that is on your formula sheet? Jesse, we don't use all 6 of these. We use 4 at a time. But basically, if I give you any 3 things, you can find the 4th. So example 2, if we want to step your car circuits, if we want to step the voltage up from the 12-volt battery in our car, your car batteries have 12 volts, but for spark plugs to spark, we need 11,000 volts. How do we do that? We have a transformer. It says our induction coil has 100 turns in the primary. How many turns should there be in the secondary? Okay, Adam, what's this asking me to find? Turns. So let's label this. I'm going to draw a little arrow. That's V primary. That's N primary. That's V secondary. And this wants me to find N secondary. Anderson, what do I know both of, 2 of, on the primary and on the secondary? Voltage. So I'm going to start there. I'm going to lift the equation, that section that says V primary over V secondary. What do I want to find, Adam? So now I'll put in the N section, which is N primary over N secondary. And then it's up to you. This is technically 1 fraction equals 1 fraction. Stuff will move diagonally. This is math 8 cross multiplying, to be honest. If you want to put numbers in and go straight to your answer, you can. I'm going to get the N secondary by itself. Adam, where is the N secondary right now? On the... Yeah. So I would say to myself, you know what? I can times that to there. I can divide the primary to the bottom, and I can times the secondary voltage to there. I'm going to get this. The number of coils on the secondary is the number of coils on the primary times the voltage in the secondary divided by the source voltage. How many coils how many turns of wire do we need in that secondary coil of wires? What do you get? It's probably going to be a fairly big number. Adam, what'd you get? So I'll go 91,700 turns of wire. Yep. Yep. Mr. Dueck, what, Adam? You said that a transformer won't work from DC current. My car battery is DC. Ah, that's a great point. We have a clever circuit that regularly interrupts the flow of current and produces a changing flux. Do you know what we call the part of your car that changes the DC current into an alternating current? That's your alternator. Spoiler alert, but that's what it does. So we have all sorts of clever workarounds to this. A transformer that increases voltage is called a step-up transformer. In a step-up transformer, voltage increases, but secondary current decreases. A transformer that lowers the voltage, that decreases the secondary voltage, is called a step-down transformer. In a step-down transformer, your secondary current goes up. So we had to decide how are we going to define step up and step down. We could have chosen to define it in terms of the current. We defined it in terms of the voltage. More coils on the secondary, step up transformer, bigger voltage, smaller current. Fewer coils on the secondary, it's going to be a step down transformer, smaller voltage, bigger current. Example 3. An ideal transformer. Why did I say ideal transformer? Because in real life, you do lose some energy to heat and things, and so the numbers don't quite match perfectly, but let's pretend that they do. Has 160 turns of wire in the primary, that's N primary, 800 turns of wire in the secondary. There's my pair. I already know I'm going to start with N primary over N secondary. I know both of those. Then they gave me the primary circuit is connected to 120 volts AC. They gave me V primary, and it looks like they want me to find V secondary. Okay. Alfie, where is the V secondary right now on the... So we can times it. Or if you want to, you could plug in the numbers and cross multiply. I really don't care. I'm going to rewrite this. I'm pretty sure it's going to be secondary voltage equals primary voltage times secondary number of coils divided by primary number of coils. It's going to end up being primary voltage 120, secondary voltage 800, primary number of coils 160. Is that right, folks? Is that right? What was the original voltage, the primary voltage? What was our secondary voltage? Is that a step up or step down? And I could have figured that out ahead of time by noticing N got bigger. If N gets bigger, V gets bigger, it's a step up. The circuit symbol for a transformer kind of looks like this. You'll notice they don't touch, and that's because no electrons from this side actually make it over to this side. What we're doing is we're using a changing flux to induce a voltage and therefore a current in this coil of wires. So this is how you're typically one of the main methods we do charging pads, indirect charging, non-plug-in charging, wireless charging. Okay? It says find the unknown current and voltages and then label the transformer as a step up or step down. Okay. What's my pair? It looks like my pair is N. So first I'll find the voltage. N primary over N secondary is V primary over V secondary. And it wants me to find V secondary. That's going to be voltage primary times N secondary divided by N primary. Primary voltage, 120. Secondary number of coils, 120 as well. Primary number of coils, 30. Joe, what'd you get? I agree. Is this a step up or a step down transformer? But you know what? There's another question mark on the picture. What else do they want me to find? Secondary or primary? They want me to find the current here? Secondary, okay. So, the one that they gave me is N's. I'll use that. I could use my V's answers, but if I got them wrong, I'll get I wrong. This one's going to be the opposite. So it's still going to be N primary over N secondary, but if you look at your formula sheet, it's I secondary over I primary. When voltage goes up, current goes down. What did you say they want me to find? I'm going to get that by itself. It's going to be, oh, again, just times the IP over. Secondary current is going to be N primary, I primary divided by N secondary. It's going to be N primary 30, I primary 2 divided by N secondary 120. You know what? It's going to be 60 divided by 120. I think I can do that in my head. Is it 0.5? Yeah. that all right? Okay. Let's try B. Find the secondary voltage. Is it step up or step down? I can already tell you it's step up. How could I tell just by glancing at this that this is step up? And got bigger. And that's also the pair that they gave me. So Caden, I'll start with N primary over N secondary equals, I guess, V primary over V secondary. Caden, what do they want me to find in this equation? Yeah, where is it right now? On the bottom. Let's do my little stuff moves diagonally. I think V secondary is going to be V primary N secondary divided by N primary. I would encourage you on a quiz or a test, write out all the numbers. By far, the biggest dumb mistake I see is kids put the wrong numbers in the wrong places because they're trying to do too much on their calculator in their head. If your homework, if you want to try going straight to the answer from here, go ahead. But on a test, I'm going to go 10 times 500 divided by 5. Is that right, Mr. Dueck? Is it 1,000? No. Yes? Is the answer 1,000? Units, it's a voltage. Volts. Turn the page. Try C and D on your own. See if we get the same answer. There's what I got for my 4 answers. And I think the answers are also in the margin next to each question. You can check. Press the OK. Yep. That look good. So let's talk about how our power infrastructure works nationwide. We ship power long distances. Oh, wow, there's my cough again. In those power lines, those big metal towers that go over the mountains, we ship it at very high voltage, usually around 1,000,000 volts. Then we send it to a power station in a town. There's a big transformer that steps it down to about 20,000 volts. That's usually what's running through the power lines in your neighborhoods. Then we run it to another transformer, step it down to 120 volts, and send it to your houses. Now, why do we do all that? Let's talk about transmitting electrical power. We could do this one of two ways. We could ship power across those power lines over the mountains at high voltage and therefore low current, or high current, low voltage. So suppose we have a generator at City A and it's delivering 1 megawatt, 1 million watts of power over the power lines. The power lines have a resistance of only 10 ohms. We made them low resistance. We're spending the money. All right. One option would be to ship this at 5,000 volts. Now, if we ship this at 5,000 volts, because power equals V times I, then I current in the wires would be P, 1,000,000, divided by V, 5,000, and you would have 200 amps of power going through those power lines. How much power would you lose to heat? To figure out how much power you would lose, we can't use V times I. We have to use the resistor of the wires and the current in the wires. We have to use I squared R. If you figure out how much power you would lose 400,000 watts. 40% of the power would be wasted. And in fact, those wires would be glowing red hot like a stove element. You're wasting it all to heat. So what we do instead, Jazz and Deep, we ship it at a much higher voltage, maybe 500,000 volts. Now if I do the same thing, I equals P divided by V, 1,000,000 divided by 500,000. Now there's only 2 amps going through the wires. Now the power loss is 2 squared times 10, or 4 watts. This is 0.004% loss. This is 99.996% efficient. That's about as good as we ever get in the real universe. We'll take that. So what we do, our whole infrastructure, we ship power at very high voltage through the big power lines. You know, the big metal towers that you see going over the mountains. Those arrive in towns. Power stations step it down to 20,000 volts because we still don't want to lose a lot of power. Ship it through the power lines to the neighborhoods, step it down again into your houses. So let's do an example, example 5. Suppose the Dueck Electric Power Company is going to ship 150,000 watts of power, and we're going to ship it over 2 ohm transmission lines at 20,000 volts. How much power is lost? Well, power equals V times I. That means I equals P divided by V. So the current is going to be 150,000 watts of power divided by 20,000 volts. On your calculator, how many amps of current will we be shipping? How many amps of current will be running through the power lines? 7.5 amps? How much power is going to get lost? Now, this involves the current heating up the power lines, which means we're going to use I squared R, not V times I, because we're focusing on the actual power lines. They are the resistance in this circuit. It's going to be 7.5 squared times 2. 7.5 squared times 2. How much power do I lose? I lose 112.5 watts of power. How efficient is this? Well, efficiency is the smaller number, 112.5, divided by the bigger number, 150,000. Now, this is how much we're losing. 112.5 divided by 150,000. We're losing, oh, my calculator displays it in scientific notation, 0.00075. Or if I want to figure out how much we're keeping, I'll just go 1 minus this answer. This is 99.9% efficient. In fact, 99.925% efficient. That's, again, Carter, about as good as we get. Yeah. Looking at the homework, answer it in the way the answer key says, probably as a percentage. I move between percents and decimals in my head. I treat them the same, so I'm not too fussy. I've got good number sets. So 99%, 99.9% efficient. What if instead we shipped it at 560 volts, not 20,000 volts? Well, let's walk through the same calculation. First, we would want to find the current, which is P divided by V. It's going to be 150,000 watts divided by 560. How many amps of current are running through the wires now? I get 267 point, I'll call it 268 amps, and I'll just store this on my calculator. What's the power loss going to be? Power loss is going to be I squared R, so it's going to be my answer button squared times 2. How much power am I going to lose if I go this button squared times, not 22, Mr. Dueck, times 2? I'm going to lose 143,500 watts of power. How efficient is this? Well, what percent am I losing? The efficiency loss is going to be the smaller number, 143,500. I'm going to use my answer button, divided by 150,000. I'm going to be losing 95.66% of my power. How much would I keep? You've learned in probability, 1 minus that. Instead of being 99.9% efficient, this is 4.33% efficient. Those wires would be glowing red hot like a stove element. You're giving almost all of your power, your work over time, your energy per second to heat. So that's why we have our infrastructure. What's your homework? I think that was the last one, wasn't it, Mr. Dueck? I got a couple of cool videos, but I'll get to them another time, I think. You can try. Every question there is good. Can you get out the ultimate review, please? We're going to cross out some questions. And this is also my way of finding out which ones of you have a copy of the ultimate review. So I'll pause for a second. Questions you can cross out. 1 is good. I like number 2. I like number 2. I like number 2. Number 2 is a nice question. I like number 3. I like number 3. I like number 3. Number 3 is a nice question. You can cross out number 4. I thought I did this already. Oh, I'm gonna have to go from memory then. Yeah, you can cross out number 4. I like number 5. I like number 5. I like number 5. I like number 6. I like number 6. Cross out 7. 7, the answers didn't photocopy. In fact, 7 is number 5. It didn't photocopy properly. 8 is good. 9 is good. 10 is good. You can cross out number 11. 12 is good. 13 is good. 14 is good. 15 is good. 16 is good. 17 is good. 18 is good. 19 is good. 20 is good. 21 is good. 22 is good. 23 is good. 24 is good. 25 is good. 26 is good. 27 is good. 28 is good. You can cross out 29. I like number 30. I like number 30. I like number 30. Number 30 is a nice question. Hint, hint. 31 is good. 32 is good. 33, 34 is fine. 35 is fine. 36 is good. 37 is good. 38 is good. You can cross out 39. 40 is good. 41 is good. 42 is good. 43 is good. 44 is good. 45 is good. 46 is good. And then you can skip the scholarship questions if you want. There you go, my angels. Transformers. Not more than meets the eye, but electrical device.